Hey guys, welcome back, and we're going to be looking today at solubility product constants. So far, we focused quite a bit on the equilibrium product constant, which helps us find concentrations of reactants in products. As a reminder, this tells us the ratio of products to reactants, right? It was always whatever your products were over your reactants. And we were always looking at the concentrations of these things. We can also look at something called the solubility product constant, which is usually written as KSP. So where this equilibrium one is Kc, or sometimes it's called KEQ, you see them both. Solubility product is KSP. Now this is a constant which is just going to tell us how much of a substance we can dissolve in water. We looked earlier in the year at solubility and just kind of like solubility charts and how to tell if something's soluble or not. We're going to really dig into the nitty-gritty of that kind of stuff today, including doing some math on it. Now here's the deal though. Solubility product constants are only used to describe dissociation reactions. So for example, I've got calcium sulfate, solid, turning into aqueous calcium ions and aqueous SO4 ion. I'm going to write that out better, SO4. And aqueous sulfate ions. So if this is the case, they give you this reaction here. They say, okay, if the solubility of calcium sulfate, you look it up in a solubility table somewhere, and it says, okay, the solubility is 4.9 times 10 to the 3 moles per liter, molar. What would your solubility product constant be? Now you can use ice charts to help you set it up, but let's look at the equation first. KSP, and here's the beautiful thing about it. It's the exact same as equilibrium. It's products over reactants. So it's going to be whatever our concentration of calcium is times our concentration of sulfate. And if you look here, neither of them have a coefficient, which means I don't need to square anything. Divided by the concentration of my product, or reactant, calcium sulfate. But one thing to note, very important thing to note, I'm going to highlight it here. Calcium sulfate is a solid, which means in this reaction, I don't need it. Solids have a set concentration. It never changes, so it's lumped into KSP for you. You don't have to worry about it. So our real equation here is that KSP is the concentration of calcium ions times the concentration of sulfate ions. So these are going to be much easier than equilibrium product constants because since they're dissociation, this side over here is almost always going to be a solid, which means you can always cut it out of the equation, which means you're not dealing with fractions. So what we have to figure out are what are these going to be? Now, I'm not going to have to use an ice chart for this one because they're telling it to us. The solubility of calcium sulfate is 4.9 times 10 to the negative 3. That means if I were to put this in water and try to dissolve it, this is what the concentrations would be of my product. That's how much of it would break down. So KSP is just going to be 4.9 times 10 to the negative 3 times 4.9 times 10 to the negative 3. Or if you want to simplify it, you could do just 4.9 times 10 to the negative 3 squared. Both should work. Let's open up my calculator here. Oh, this is going to get real finicky soon. Okay. Oh, right. I can't do powers on this calculator. All right, fine. I will have to use my handheld calculator, but I'll try and read out what I'm doing here. So I'm typing in 4.9 times 10 to the power of 3 negative equals. And I get the answer of... And then I'm just going to square that. I'm not going to bother doing this long one because that's more likely that I'm going to screw something up. So hit the squared button. And my solubility product constant is 2.401 times 10 to the negative 5. So a very small KSP, less than 1, which means which way does this reaction lean? It's the exact same as KEQ. It prefers calcium sulfate, not ions, which means calcium sulfate, not super soluble. You're not going to have a lot of ions in water because this equilibrium, if you want to think about it that way, prefers to be on this side. It prefers to stay as a solid instead of breaking into ions. All right, let's look at one where we actually do have to use an ice chart, just so you can see what it looks like. I got lead chloride breaking down into lead 2 plus and 2 Cl minus aqueous. All right. Calculate the solubility. So now they're going to give us KSP. We need the solubility. So I'll start with the reaction over here so you can see the equation, and then we'll see why we should probably ice chart this one. KSP equals the concentration of lead times the concentration of chloride. And keep in mind, I got to check my mole ratios. It has to be the concentration of chloride squared. All right. Now I know what KSP is, so I can write that one in. It's 2 times 10 to the negative 5. All right. But now I got a couple things I don't know yet, so I can't really solve this until I know what one of those concentrations at least would be. So let's do it like an ice chart. Now keep in mind that I ignored the PbCl2 over here on purpose because it's solid. I don't need to put it in because it's a solid. So it's not like I forgot about it. It was an intentional choice. I don't want it. It's solid. So I only have to look at my Pb2 plus and my Cl minuses. All right. So if I dump PbCl2 into water, well, I know that I'm initially starting with 0 of this stuff. I'm going to gain some Pb2 plus, and I'm going to gain 2 times that amount of chlorine, because mole ratio, right? We got the 2 up here still. Hasn't changed. So at equilibrium, what's going to happen? Well, Pb will change by x, chloride will change by 2x. And this is what we're going to have to punch into our equation. So let's do it. Pb2 plus was an x. Oh, whoops. 2 times 10 to the negative 5 equals x times 2x squared. All right, let's do a little bit of algebra here. X times 2x squared is just 4x squared, which means 2 times 10 to the negative 5 equals x times x squared gives me x cubed. I got no numbers, so the 4 stays the same. All right, time to solve this one. Grab the calculator. 2 times 10 to the power 5 negative equals, so I have my number there. I'm going to divide both sides by 4. So I'm left with 5 times 10 to the negative 6 equals x cubed. Now, I don't know if you've seen this one before. If you haven't, you can get rid of a cube by using a cube root. So it usually looks on a calculator like this if you have a cube root button. Sometimes it'll look like this, and you'll have to press that button and then hit 3 to make it cube root. What you should do to test this out, I'm going to do this in blue. Try to find the cube root of 8 in your calculator. The answer should be 2. So find out what series of buttons you have to press to turn the cube root of 8 into 2. Once you know that, you're going to find the cube root of 5 times 10 to the 16. I just have a cube root button, which makes it real easy. And it turns out that x is 0.017. Or if you like scientific notation, 1.7 times 10 to the negative 2. And so that's actually going to be our molar solubility. That's what x is. That's going to be our solubility per a single mole. So you can see that Pb changes 1 mole at a time. So that's our molar solubility. If I wanted to find what it would be for chlorine, I'd find what this is by multiplying it by 2, but then I'd have to divide it by 2 because of the mole ratio. So multiply by 2, divide by 2, doesn't matter. You basically just got to find what x is, and you should be good to go here. And that's it. That's all we got for KSP. It's if you've done the equilibrium charts and they were pretty easy, this is just, well, not really easy. These charts get a little complicated, but this is just an easier version of that because your expression won't ever have a fraction involved. Sometimes you will get cubes, or worse, 4s or 5s if you're really unlucky, but you just root those and they should disappear. You shouldn't have to deal with fractions most of the time because this is a solid, and so you won't have to include that in your math anytime, which makes things so much easier to deal with. But anyway, that is solubility product constants. So if you have any questions, you know where to find me.